Okay, so I'm just going to go through my notes for today's lecture briefly. So today we're going to be talking about transfer functions, and the basic idea of a transfer function is it acts between your input and your output. So it takes your input voltage to your output voltage, and it's your circuit. Okay, so this is going to be a filter. You're going to have a source at one end, and you're going to have a port that you're measuring your output voltage on. And the transfer function basically characterizes the circuit for sinusoidal steady state. So if we plot Vn versus time, and I plot in blue here the V in curve, and you notice that it's a sinusoidal steady state type curve, but it's not a cosine. I could have made it a cosine by just changing the definition of time zero, but I decided I wanted to keep it more general than that. And you see it has a certain amplitude and it has a certain phase. If we plot V out now in the green, okay, sorry if you have trouble seeing colors, but it's the lower amplitude one, and what you'll see is that it's phase shifted, in this case a little bit in advance of the previous signal, and it has a very different amplitude. So we have changes in amplitude and changes in phase, but not changes in frequency. That's important. The frequency of these two signals is exactly the same, and that's because it's a linear circuit. And so we can go back a little bit and figure out differential equations and all of that and prove that, but basically that's the bottom line. So the question is now, can we find for a specific circuit, let's take a circuit here driven with a sinusoidal signal, a resistor, and take the voltage across the capacitor to be the output. This is going to filter the frequency, so the output is going to depend on the frequencies. Can we find the ratio of the amplitudes of V out to V in and the change in phase of the output relative to the input? And if we can do that, we don't need to do a lot more math. In fact, we usually don't care about much more than that if we have sinusoidal signals. So you have to think in the complex space of complex signals, and of course you have to remember that we're going to have to take the real part at the end. So if we have a complex voltage which consists of a complex amplitude and some drive frequency, again, if we just set our time zero to be such that this is a cosine, you can have that be a real number already, but let's just assume more generally it's complex. Then the input voltage is just the real part of this signal. And so now let's go back and try to figure out what that phase is. So if we look at the output is also going to have that same transform done to it, where the output amplitude is going to be a complex number. What we're basically asking is the ratio of the magnitudes of these two amplitudes, this V out over this V in, the magnitudes of that, and then the ratio of the two phases, so whatever the phase of this complex number is minus the phase of that complex number. They're both oscillating with e to the j omega t, but they also have some other phase, and we're interested in the difference of those two phases. And again, to get the actual output voltage, we're going to have to take the real part of this complex voltage. That's just a reminder that isn't that sort of becomes second nature after a while. So the transfer function, which is just the output complex amplitude to the input complex amplitude, and it's got this form. And why is it that form? Let's go back up for a second. It's just because this is a voltage divider in the world of complex notation, and it's a voltage divider, I'll add a little note here, that has complex impedance 1 over j omega c. And so if we treat this as just two resistors in series with a DC drive, it would be this resistor divided by the sum of the two resistances. So now in the impedance space, it's that 1 over j omega c impedance divided by the sum of the two impedances. And so we can just multiply by j omega c in the bottom and the top, and we get a form like this, and we can factor out the 1 over rc, and we get a form like this. This form is really important. That j omega being out front, that's quite a standard form that we write these transfer functions in. We just have a j omega term and then plus another term, and then we'll typically, if they're more complicated, you might chain together multiple factors of this form. All right, so what is that? Oh, went too far over. Give you a little preview. So here we have an output voltage divided by input voltage in terms of magnitudes. That gives you the magnitude of the transfer function. So we're solving the first part of the question here, which was to find the ratio of the magnitudes. And here we have 1 over RC. And we've just calculated it out. If we go back for a second, sorry about all the moving around, but it's we're trying to find the magnitude of this. Well, we have a complex number in the denominator. When you take the magnitude of a complex number, it's just the square root of the real squared plus the imaginary part squared. If you think of it on the complex plane, it's basically using the Pythagorean theorem to find the length of a phasor in the complex plane. So you do that, the 1 over RC stays out in front, you get something like this. Right, what is this delta phi now? Well, it's easier to think about it in terms of polar notation. So in polar notation, in general, let's suppose we have a complex number. Of course, this is our V out, but you don't have to pay attention to that. And another complex number, of course, I mean this is our transfer function, but it's a more general statement that I'm making here, times a complex number, which is, of course, our V. And again, that's not that relevant to the statement here. If we write all these in polar notation, the critical part is writing this transfer function in polar notation. That transfer function polar notation is just its magnitude times e to the j times the argument of h. And when you do that, what you find is the change in the phase, so you just divide both sides by e to the j phi 1 minus phi 2, and then compare the arguments, and you'll see the only thing left on the right that's not real is this e to the j argument of h, and so the argument of h is just equal to the change in the phase. That's actually, I think, more easy to visualize graphically, so you can try that on your own. Okay, so the analytic form of that argument is this arctan2 function, which is basically a regular arctan, but we keep track of the y component and the x component separately so that we avoid redundancy in the choice of quadrants for the solution. If we go back now to the transfer function, which was over here, so if you just look at the denominator, you can see the imaginary part is omega, imaginary part is omega, real part is 1 over RC. All right. So we take the imaginary part here, omega, real part 1 over RC. Where did the minus sign came from? Well, in the transfer function, the omega plus j omega plus 1 over RC was in the denominator. So we're interested in the polar angle of the function itself, not just its denominator. And so when you take an exponent from a denominator to a numerator, you multiply the angle by the minus sign, which is, we could put a minus sign out here, I just put it on the y variable. Okay, so what are the important frequencies in this filter? Well, if we look here at the magnitude, you can see that these two terms have comparable magnitudes when omega is 1 over RC. And so that's kind of the only important frequency that we can identify. So we'll pick that as a special point. Omega b is 1 over RC. It's kind of the only term in the problem which has units of frequency, is another way to think about it. So of course, we're also interested in how things behave below this frequency and how things behave above this frequency. In fact, we're interested in all frequencies. What's important is that these behaviors can be lumped into 3 categories. And we call this the break frequency. So for reasons we'll get to later. So we have to go through a little bit of a laborious process of figuring out what the different frequencies are. So I'm just shifting the page over here. We can see what our transfer function is. It's got the form 1 over j omega plus 1 over RC. So if we go back here, we see that at low frequencies, right, this j omega is negligible relative to the 1 over RC, and so you just get 1 over 1 over RC, and that cancels with the 1 over C, and you get 1. At omega is equal to 1 over RC, then the 1 over RC factors out, and you get 1 over j plus 1, and at omega much, much larger than 1 over RC, if we go back to this form, you'll see that when omega is really, really large here, we can neglect this 1 over RC, and we'll end up with 1 over j omega RC. All right, so that's that. The magnitude of h, why are we caring about the magnitude of h? Well, remember, we cared about the ratio of the periods, not the period itself. So, sorry, the ratio of the amplitudes. So that magnitude of h is just the ratio of the amplitudes. it doesn't have any phase information in it. So interesting, at low frequency, there is no ratio. They're equal to 1. They're equal to each other. So there's no effect at low frequencies. That actually makes sense if you look at the circuit for a second. At low frequencies, this is a capacitor. Low frequencies, it acts more or less like an open circuit for the incoming signal. And so you just get no current flowing, though no voltage drop in the resistor, so the output voltage is equal to the input. At higher frequencies, the magnitude is 1 over square root of 2. And then at very high frequencies, it's going to be 1 over omega RC. This kind of makes sense too, just because you're going to have this acting like a short circuit at high frequencies, and so the input is going to be substantially attenuated. You notice we could have put 0 here. I mean, at these very high frequencies, presumably if omega is infinity, this is approximately 0. But we're still interested in the frequency dependence, so we're going to, so we're basically interested in the largest non-zero term here, and that's the 1 over omega RC. If we take the logarithm of this, just by convention, people take the logarithms, what you'll find is minus 0.15 minus log omega minus k. If we take 20 times the logarithm, what we see is it's still going to be 0. The log of 1 over square root 2 times 20 is minus 3, and we use units of dB. This minus log of omega minus k is like the log of 1 over RC. That just changed to 20 times. And then the argument of h, well, I'm not sure if it's easiest to look up here or not. For low frequencies, you're going to see that this is going to be actually probably the best place to look is right here. At low frequencies, this is the real term. So the log, 20 times the log of that term is going to be, sorry, not 20 times. The argument of it is just a real number, so the phase is 0. This is a number j plus 1, which is a 45-degree slope on the imaginary plane, but now it's reflected because it's in the denominator. So it's going to be minus pi over 4. And this is minus j, so it's pointing straight down in the imaginary plane. It has a phase of minus pi over 2. So I didn't give you parameters to start with. I could have, say, a kilo ohm and a nanofarad. I would give you a break frequency of 10 to the 6 radians per second. Now notice that's not a real frequency in hertz per second, cycles per second that you would normally work with a function generator, so be careful about factors of 2 pi. This is 2 pi times that natural frequency. All right, so where does that leave us? So we can actually do this plot. It's a fair amount of work, so I just transferred some of the points. So at 10 to the 6, I gave the minus 3 dB. We had that from down here, okay? And then at the delta phi is the angle of h, we had this phase shift. We went from 0 to minus pi over 4 to minus pi over 2 as we went through the break frequency. So we're going from 0 to minus pi over 4 to minus pi over 2. Now we did a 3 dB. Now an interesting thing is the high frequency behavior. We calculated in the table below that the slope at the high frequency would be a linear dependence on log omega, and it would have a slope of minus 20. Notice here I plotted omega, but I plotted it on a log paper. So this, even though it looks like line paper, it's not. It's got a logarithmic progression here because I've written down factors of 10. Similarly here, this is omega, and I've written down factors of 10. And what you see up here is, for that reason, it's linear here. It has a slope of minus 20. How do we interpret that? Well, it means that the filter attenuates 20 dB for every factor of 10 increase in frequency. Now an octave is a factor of 2 increase in frequency, which is about 10 is about 2 to the 3, so we can approximately divide this by 3 and find that there's a 6 dB attenuation per octave increase. This is a standard filter response for a first order filter. This would be called a first order low pass filter, sorry. First order low pass filter. And very characteristic, it has a low frequency behavior, then it has a knee where there's a 3 dB attenuation or a 0.7 if you want to look in the amplitude space, and then a roll off of 60 dB per octave. Also very characteristic is a pi/2 phase shift. In this case, the output is shifted by -pi/2, which basically means that it will lag the input frequency. So you would write it as like cosine omega t was the input, it would be cosine omega t minus pi/2 would be the output. All right, so that's the summary of first order Bode plots. Just to quickly go through what we did, we started with the idea that we have a circuit and an input and an output. We want to figure out what the ratios of the amplitudes are and what the difference of the phase is. We chose this particular RC network. We then calculated the transfer function. We used that transfer function to determine the magnitude of the amplitude and the argument of it, and we did it at a series of points, of special points, and then we plotted that transfer function and discussed the roll-off at the high frequencies as being in terms of decibels per octave.